quantum sciences have captured our imagination and reshaped our understanding of the physical world in ways that astonish both scientists and curious minds alike. In this video, we explore the captivating world of quantum sciences, a subject that lies at the intersection of philosophy, physics, and technological innovation. Our journey covers the origins of quantum ideas, the fundamental principles that shape this field, and the remarkable experiments that reveal its mysterious nature. Whether you are a dedicated science enthusiast or simply curious about how nature works on its tiniest scales, the discussion ahead is crafted to be both accessible and engaging. We will explain how the smallest particles follow rules that defy everyday intuition while forming the basis of everything around us. As we introduce key concepts such as wave-particle duality, superposition, and entanglement, our aim is to make these ideas clear through relatable examples and analogies. Understanding quantum mechanics is not about memorizing abstract formulas. It is about appreciating a new way of seeing the world, where certainty gives way to probabilities and challenges traditional logic. This exploration demonstrates that even the most perplexing theories can illuminate practical technologies, including lasers, medical imaging, and the emerging field of quantum computing. By uncovering these ideas, we invite you to view science as an ever-unfolding story of discovery and wonder. With a friendly tone and clear explanations, this video seeks to demystify quantum phenomena and inspire further inquiry. Let us delve into the intriguing world of quantum sciences and explore a realm where conventional rules break down, yet beauty and logic combine in unexpected ways. I invite you to embark on this scientific adventure with curiosity and excitement as we uncover the secrets that define our universe and learn how even the strangest ideas can lead to advancements in our lives. Quantum science did not emerge overnight. It arose from centuries of scientific inquiry and transformation of ideas. Early scientists grappled with the limitations of classical physics, which had long explained everyday phenomena, but failed to illuminate mysteries at the atomic scale. Discoveries in the late 19th and early 20th centuries prompted a paradigm shift that paved the way for quantum theories. Pioneering figures such as Max Planck, Albert Einstein, Niels Bohr, and Erwin Schrödinger challenged the conventional views of matter and energy with their groundbreaking research. Their work proposed that energy is quantized and that particles can exhibit both wave and particle characteristics. Each breakthrough built upon previous insights and often encountered resistance from those who found it difficult to embrace a new way of looking at the universe. The shift from classical to quantum thinking was not merely a scientific revolution, but also a philosophical one, inviting questions about the nature of reality and observation. As experimental evidence accumulated, including evidence from the photoelectric effect and atomic emission spectra, the scientific community began to accept that the universe operated on principles far more counterintuitive than our everyday experiences had suggested. The evolution of quantum theory represents a fascinating narrative of innovation, debate, and perseverance. History shows us that quantum sciences emerged from a rich dialogue between theory and experiment, where each discovery opened doors to further questions and deeper understandings. By tracing its development, we appreciate how ideas that once seemed speculative became the foundation for the modern fields of physics and technology, reshaping history and our place in the cosmos. Reflecting on this storied past, we see that each revolutionary idea and experimental milestone contributed to a tapestry of scientific progress. This inspiring history continues to encourage new generations to explore the unknown, a legacy of endless wonder. At the heart of quantum mechanics lies a set of principles that challenge the way we think about nature. One key idea is wave-particle duality, which means that tiny particles such as electrons and photons sometimes behave like particles and at other times display wave-like properties. This surprising duality emerged from experiments that revealed interference patterns even when particles were sent one at a time. In simple terms, imagine throwing a pebble into a pond and watching the ripples form. Quantum entities can produce similar patterns, yet they also seem to pass through space as discrete packets. Another fundamental principle is quantization. Unlike classical systems where energy can vary smoothly, quantum systems exist in discrete states. This principle, first hinted at by Max Planck, tells us that energy exchanges happen in fixed amounts, similar to counting individual steps rather than measuring a continuous slope. This idea revolutionized the way scientists viewed light and matter, prompting the development of new theories and models to describe atomic behavior. Superposition is a concept that truly defies everyday experience. In a quantum system, a particle can exist in multiple states at the same time, only settling into a definite state when measured. To illustrate this, think of a coin spinning in the air. Until you catch it, the coin is not simply heads or tails, it holds the potential for both outcomes simultaneously. Entanglement is another remarkable phenomenon in which two particles become linked so that the state of one immediately influences the state of the other, regardless of the distance separating them. Einstein famously referred to this as spooky action at a distance. In everyday language, it is as though two friends share a secret that instantly changes their behavior no matter how far apart they are. Although this sounds mysterious, experiments have consistently confirmed entanglement, and it remains a cornerstone of modern quantum research. The uncertainty principle, introduced by Werner Heisenberg, explains that certain pairs of physical properties, like a particle's location and momentum, cannot both be known exactly at the same time. The more precisely one property is measured, the less precisely the other can be determined. This counterintuitive limit is not due to flaws in measuring instruments, but is an innate feature of the quantum world. Mathematical frameworks underpin these concepts, providing a language to predict probabilities rather than certainties. Instead of a particle following a clear path, quantum mechanics uses wave functions to describe the likelihood of finding a particle in a particular place at a given time. These probabilities emerge naturally from the mathematics, offering a reliable guide to experimental outcomes. While the math itself can be intricate, the underlying ideas give us a fresh perspective on the behavior of nature at its smallest scales, inviting us to reimagine reality in a more nuanced way. These principles, while challenging to intuit at first, open up a realm of possibilities that continue to reshape technology and our understanding of reality. Understanding these fundamentals enriches our view of the universe and bridges the gap between abstract theory and observable phenomena. Each principle, from duality to uncertainty, not only deepens scientific inquiry but also sparks innovation in everyday technologies. By connecting these sophisticated ideas to familiar experiences, we appreciate that quantum mechanics is not a distant or esoteric field, but a window into the underlying order of nature. This clarity allows us to see that even when the rules seem unpredictable or strange, they follow a consistent logic that has been verified through careful experiments over many decades. In sharing these insights, we communicate the excitement and wonder quantum theory inspires worldwide. Experiments have always been the driving force behind our understanding of quantum phenomena, and several key experiments have played a pivotal role in shaping the field. The double-slit experiment, for instance, has become one of the most famous demonstrations of wave-particle duality. In this groundbreaking experiment, particles like electrons are fired at a barrier with two openings, and an interference pattern emerges on the screen behind the barrier. This result perplexed scientists because it suggested that each particle behaves as if it passes through both slits simultaneously, leading to patterns typical of waves. Another influential experiment is the Stern-Gerlach experiment, which provided early evidence concerning the quantum property known as spin. In this experiment, a beam of particles is passed through a non-uniform magnetic field, causing the beam to split according to the orientation of the particle's intrinsic angular momentum. The clear separation into distinct spots on the detector rebuffed the classical notion that a particle's orientation would be random or evenly distributed. This experiment not only confirmed the quantized nature of spin, but also paved the way for future research into atomic magnetism and quantum state measurement. Recent breakthroughs in experimental quantum physics have continued to astonish the scientific community. Technologies involving ultra-cold atoms, for example, allow scientists to observe quantum effects on macroscopic scales, and experiments with entangled particles have further solidified our understanding of non-local interactions. These cutting-edge experiments demonstrate that even the most counterintuitive quantum effects can be observed and harnessed under controlled conditions. Overall, these experiments validate quantum theories by providing tangible evidence of phenomena that once seemed purely theoretical. They serve as concrete examples of how careful observations can challenge and ultimately expand our understanding of the physical world. Through the consistency between experimental results and quantum predictions, our confidence in these revolutionary theories has grown, ushering in a new era of technological innovation and scientific inquiry. Each experiment, from historical demonstrations to modern cutting-edge tests, builds a bridge between abstract theory and real-world observation. The meticulous design and execution of these studies have not only confirmed long-held hypotheses, but also opened new avenues for research. With every experiment, our grasp of quantum phenomena becomes clearer, inviting us to explore further and innovate in unexpected ways. These pivotal experiments encapsulate the spirit of discovery that drives science forward and remind us that even the subtlest observations can revolutionize our comprehension of the universe. Absolutely. Quantum sciences have already started to revolutionize various fields through innovative applications that harness their unique properties. One of the most exciting applications is quantum computing. Unlike classical computers that use bits to process information, quantum computers utilize qubits, which can represent both 0 and 1 simultaneously. This ability, rooted in superposition, promises to solve complex problems at speeds far beyond today's computers. Industries ranging from pharmaceuticals to finance are investing in quantum computing research, anticipating breakthroughs in optimization, simulation, and data analysis. Another important application is quantum communication. By exploiting principles such as entanglement and quantum key distribution, quantum communication systems offer unprecedented security. In these systems, any attempt to intercept a message alters its state, immediately alerting the users. This feature makes quantum communication a promising solution for secure transmission of sensitive data, including financial transactions and personal information. As technology advances, the development of global quantum networks could lead to a new era of secure, instantaneous communication that rivals current internet capabilities. Quantum sensors also represent a frontier of technological innovation. These sensors operate by measuring minute changes in physical quantities, such as magnetic fields or gravitational variations, with extreme precision. Applications range from geological surveying and environmental monitoring to medical diagnostics and navigation systems. For example, quantum imaging methods are being developed to detect early signs of diseases, offering the possibility of earlier diagnosis and improved patient outcomes. The sensitivity of these sensors often surpasses traditional devices, opening new opportunities for research and practical use. Beyond specific devices, quantum technologies are influencing the broader landscape of science and technology. Advances in quantum mechanics have led to the creation of new materials with extraordinary properties, such as superconductors and novel topological insulators. These materials not only deepen our understanding of physical laws, but also pave the way for next-generation electronic devices and energy-efficient systems. In the realm of medicine, quantum insights are contributing to the development of innovative imaging techniques and targeted therapies that promise more precise treatment with fewer side effects. Real-world examples of quantum technology in action are becoming increasingly visible. Several startups and established tech companies are developing quantum algorithms that optimize logistics, forecast weather, and even improve artificial intelligence. In laboratories around the world, experiments with quantum dots and other nanoscale structures are leading to advancements in display technologies and high-resolution imaging. Moreover, collaborations between academic researchers and industrial partners are accelerating the transition from theoretical models to practical applications, ensuring that quantum science continues to benefit society at large. Looking ahead, the impact of quantum technologies is expected to grow even further. As research moves from the lab into everyday use, we can anticipate a surge of innovations that will transform industries, enhance security, and redefine our understanding of information processing. The potential for revolutionary change is vast, and the ongoing integration of quantum principles into technology is setting the stage for a new era of scientific discovery and economic growth. Every advancement in quantum technology not only pushes the boundaries of scientific capability, but also drives economic development and societal progress by unlocking solutions to problems once thought unsolvable. As we continue to explore and implement quantum applications, the convergence of research, industry, and government will accelerate innovations that reshape our world in profound and lasting ways. Quantum future starts now. As quantum sciences evolve, the horizon of discovery expands into new frontiers of research and potential applications. Future directions include developing more powerful quantum computers, advancing quantum communication networks, and creating ultra-sensitive sensors that can detect phenomena with unprecedented accuracy. Researchers are also investigating how quantum principles might revolutionize fields such as medicine, materials science, and cryptography. Alongside technical progress, ethical considerations play a crucial role in shaping the future of quantum technologies. The immense power of quantum computing, for instance, raises questions about data privacy and security, challenging existing norms of digital protection. Furthermore, as quantum systems become integral to communication and national infrastructure, there is a growing need for international guidelines and regulatory frameworks to ensure responsible use. Balancing innovation with ethical stewardship is essential for maximizing benefits while mitigating potential risks. Scientists, policymakers, and society at large must work together to address these challenges. By fostering open dialogue and establishing clear ethical standards, we can ensure that the quantum revolution proceeds in a manner that is both groundbreaking and socially responsible, paving the way for a future where technology and human values coexist harmoniously. Such proactive efforts will guide the ethical integration of quantum innovations for future. Our journey into quantum sciences has revealed a landscape filled with wonder, challenge, and immense possibility. We have navigated through the historical evolution of quantum ideas, explored the fundamental principles that defy classical logic, and witnessed experiments that have reshaped our understanding of the universe. Along the way, we have seen how quantum mechanics is not an isolated realm of abstract thought, but a dynamic force driving real technological innovations. From quantum computing to secure communication and ultra-sensitive sensors, these breakthroughs are forging a new path toward a future where science and technology transform our daily lives. As we look ahead, the promise of quantum research challenges us to rethink what is possible and encourages collaboration across diverse fields. It reminds us that every scientific endeavor, no matter how counterintuitive, carries the potential to unlock extraordinary capabilities. By embracing both the empirical and philosophical dimensions of quantum sciences, we gain valuable insights into the true nature of reality. Let us take away a sense of curiosity and determination to explore, innovate, and apply these principles responsibly, ensuring that the quantum revolution benefits all sectors of society. In summary, quantum sciences inspire us to pursue knowledge and create a brighter tomorrow.